Hello there, Mr. Sutton here with the BC Calculus 618 Part 1 homework solutions on logistic growth. For this problem, we've got this logistic equation describing the growth of a population of creatures, and we want to figure out a few things about it. First off, the carrying capacity of the population. Well, since we're already in this something times p times something minus p form, since there's no fraction in here with the p, we can actually just pick this 700 right out of there as the carrying capacity. So that's 700 creatures for that. Size of the population, when it is growing the fastest, that's always half the carrying capacity. So that's going to be half of 700, which is 350 creatures. And the rate at which the population is growing when it's growing the fastest, well, this is the rate of growth in general, this differential equation. In order to figure out the exact number, though, we need a p-value. Well, it's growing the fastest when p, the number of creatures, is 350. So we'll just plug 350 in for all the p's, and we'll just use the calculator to figure out the exact number. So plugging all that in, we end up with 98. So the rate is going to be 98 creatures per year. On this problem, we've got a logistic equation describing growth of a population of creatures. We want to know, for part A, the carrying capacity of the population. Since this isn't already in Kp times m minus p form, our carrying capacity is just this m value here of 800. So 800 creatures. And then the size of the population when this thing's growing the fastest, that's just going to be half the carrying capacity, always is. So half of 800 is 400 creatures. And finally, the rate at which the population is growing when it's growing the fastest. Well, we're going to take this 400 we just found when the population's growing fastest and plug it back in for p to get an actual rate out of that. So let's just use the calculator to see what all that comes out to. And plugging all that in gives us a rate of 320, and that's going to be creatures per year. For this problem, we want to know the carrying capacity, size of the population when this is growing fastest, and the rate at which it's growing when growing the fastest for this logistic equation describing some creatures growing. So let's start off with our carrying capacity. That's just going to be, since this is in Kp times m minus p form, that's just going to be this m value here, 1,200 creatures. Population is growing the fastest at half of that level there, so 1,200 over 2, or 600 creatures. The rate at which the population is growing the fastest is just going to be whatever you get from this differential equation when you plug in that 600 we just found, because that's the size when you're growing fastest, and this takes a p-value. So plugging in 600 now on the calculator, that's all going to come out to 72 creatures per year. On this problem, we're given this logistic equation describing the growth of a population of creatures, and we want the carrying capacity to start off with. This is already in Kp times m minus p form, although this is kind of a weird k value, but hey, let's roll with it. So that means we have a carrying capacity of m, whatever's here, this 5,000 value, so 5,000 creatures. The size when this is growing the fastest will be half the carrying capacity. 5,000 over 2 gives us 2,500 creatures. And the rate we're growing when we're growing the fastest is just whatever we get when we plug in this size for p in the differential equation. So let's use the calculator to find that. Plugging all that in, we end up with 62.5 creatures per year. For this problem, number of moose in a national park is modeled by the function m that satisfies the logistic differential equation, dm over dt equals all this craziness, where t is time in years and m of 0 equals 50. All right, that's awesome. We want to know the limit as t approaches infinity of m of t. So the key on this one, two keys. First, realizing that you're dealing with a differential equation. So when I ask for the limit as time approaches infinity of this population, I'm really just talking about the carrying capacity based off this differential equation. So there's going to be some number that we can just pick out of this if we've set things up correctly. The other key to dealing with this one is realizing we're not in Kp times m minus p form. We've actually got this fraction going on in here. So in order to make it so that I have just an m instead of an m over 200, I have to factor a 1 over 200 out of this parentheses. So I'm essentially dividing everything inside by 1 over 200, which means I'm multiplying everything inside by 200, the reciprocal. So I've got a 1 over 200 that comes out below the 0.6, and inside I have 200 minus m. Now that I've put this in Kp times m minus p form, which is kind of weird to say because p is really m in this setup, but anyway, I've got a carrying capacity of this 200 right here. And that is really what we're talking about for the population when limit of the t approaches infinity. So this is just going to end up being 200, b. For this problem, rate of change, dp over dt of number of people on a beach, is modeled by a logistic differential equation, they're telling us. And the max people allowed on the beach is 1,200. At 10, the number of people is 200, increasing at a rate of 400. Which of the following diffEQs describes this situation? So the key here, right in the beginning, they said this is a logistic differential equation. I don't know what all the different things I need to plug in are, but I do know that my standard logistic differential equation is going to be k times p parentheses m minus p. So in this case, I have an m value of 1,200 because that is my carrying capacity for this beach. The maximum number of people allowed on the beach is 1,200. This is it. All right, so I still need to figure out the k value. If you look at the answer choices, we've actually got 1,200 minus p in all of the parentheses. So really, it just comes down to that k value. You'll also notice, though, we can actually eliminate some of these pretty early. A, for example, doesn't have a p outside the parentheses, so that's got to go. B also doesn't have a p out here, but we still have to narrow it down between C, D, and E. So trying to find that k value, that means that I'm going to have to figure out values for p and dp over dt to plug in so I can go back and solve for k. Well, that's this other piece of information they gave us. At 10 a.m., and the time doesn't really matter, but whatever, the number of people on the beach is 200, so that's a p-value of 200, and then they said increasing at a rate of 400 people per hour. So when dp over dt is 400, we can plug in 200 for p. So we'll write 400 equals k times 200, parentheses 1,200 minus 200. Now we just go back and solve for k. And this was a no calculator question. Actually, this was a calculator question, so you could use a calculator on this, but we don't really need one. So if we divide both sides by 200, right away we have just 2 on the left side. Over here, this is just 1,000, so we're doing 2 over 1,000, which we could reduce to 1/500th. So you could use a calculator, didn't need one though. All right, so plugging that back in now, we can now write dp over dt equals 1 over 500 p times 1,200 minus p. Looking at our answer choices, that matches perfectly with answer choice C. On this problem, we have a population changing at a rate modeled by this differential equation, and we want all values of y for which the population is increasing at a decreasing rate. So this is a very difficult question to do if you don't realize you're dealing with a logistic function. This is logistic. This is in kp times m minus p form, pretty standard logistic function. Don't really have to do anything to modify it, but you have to realize what the shape of these things is. So you start off going concave up, and then about halfway between the starting value and the carrying capacity, halfway to the carrying capacity, you end up going concave down. So we're concave down between the middle y value and the cap, the carrying capacity. What is our carrying capacity on this? It's 1,000. This is already in kp times m minus p form, so the carrying capacity is 1,000. This population is capped out at 1,000. That means between 500, which is half of this, and 1,000, we're going to be concave down in terms of how this thing is growing. So concave down for 500 to 1,000 means we're dealing with choice C. For this problem, we're given this logistic differential equation here and an initial value of n of 0 equals 105. We want to know which statement here is false. So 3 of these are true. All right. Before I do anything else, I notice that this is not quite in kp times m minus p form. We've got this fraction here with the output variable. I want this output variable inside this parentheses to just be itself without anything else attached. So I'm going to factor out a 1 over 850 from this parentheses. That's going to give me an n over 8,500 outside. And inside now, I'm essentially dividing everything in here by 1 over 850, so multiplying by 850. Inside, I've got 850 minus n. And now that I've set things up like this, I can easily pick out my carrying capacity of 850. So looking at my answer choices, I see here that choice A, limit as t approaches infinity of the output, is 850. Well, if our carrying capacity is 850, then this is going to be true. 850 is going to be the cap. Next one, our differential logistic function has a maximum value when n equals 105. Okay, so this is talking about when you're growing the fastest. With logistic functions, we recognize that that is going to be halfway to the carrying capacity. So it's actually going to be 850 divided by 2, 425, where the max growth is happening. So because it's halfway to the cap, 105, which is not halfway to the cap, is not the maximum value for this differential growth here. Moving on then, they're telling us the second derivative is 0 when n equals 425, and that is true. This is essentially saying you have a point of inflection when n is 425, and we do have a point of inflection halfway to the cap. So this is totally true. And finally, the last one, when n is greater than 425, dn over dt is greater than 0, and the second derivative is less than 0. So essentially saying when you get to that halfway point, you are growing, because your derivative is positive, but at a decreasing rate, because your second derivative is negative. So you're essentially saying you're concave down, but still growing. And this is also true, still increasing but concave down after the halfway value. So choice B then totally is false, and we are done. For this problem, we have a population of wolves modeled by the function p according to this differential equation. And initial value of p of 0 equals 1,000. Which of the following statements will be true? So first, I notice this is not in kp times m minus p form. We've got a p over 5,000 instead of just plain old p. So I'm going to go ahead and factor 1 over 5,000 out of this parentheses to put it in that standard form. So that means I have 5 over 5,000, or 1 over 1,000, outside this thing with a p. Inside, dividing by 1 over 5,000 is really multiplying by 5,000. So inside, this is going to be 5,000 minus p. Now that I've got this in my standard form, I can go ahead and pick out my carrying capacity of 5,000. So the wolves can't get any bigger than 5,000 according to this growth model. Looking at our choices now, option 1, limit as t approaches infinity of the population is 5,000. Well, we just figured out the carrying capacity is 5,000. So that is definitely true. Okay. And we'll say m equals, because that's my carrying capacity variable. Doesn't really matter, though. It's true. All right. So second choice, dp over dt is positive for t greater than 0. And this is going to be true. We know this because it's logistic growth, but also they're telling us we have an initial value at of a population equaling 1,000. So if your initial population is less than the carrying capacity, that means you're growing up until you get that carrying capacity. So this function is always growing, and we know that because of this initial value. Now, if this initial value had been above the carrying capacity, then logistic growth actually drags you down to the carrying capacity. But because we were starting lower, we could only go up. Last one, second derivative is positive for t greater than 0, and this is going to be false. We have a point of inflection at half the carrying capacity at 2,500, after which your second derivative is going to be negative rather than positive, after which you are increasing but at a decreasing rate as you slow down approaching that carrying capacity. So when all was said and done, only options 1 and 2 were correct, so choice C for the overall answer. For this problem, we want to know which graph is the solution to the differential equation given here, logistic differential equation, and they're giving us an initial condition of y of 0 equals 100. All right, well, we can definitely eliminate some of these right away. A and C, for example, are not even a logistic shape. For that, we would need B and D. D kind of looks better between the two of them, but B is technically a logistic shape just coming from the top above the carrying capacity. So we have to take them both seriously. But now they also gave you an initial condition of y of 0 equals 100. Well, looking at these two graphs, the only one with a start value of 100 is choice D. Choice B has a start value of 500. So you actually could eliminate everything and choose choice D right off the bat. But let's go a little further and just make sure we're right. So analyzing this differential equation, we're not in Kp times m minus p form because we have our y value has a 500 underneath. So I'm going to factor a 1 over 500 out of that parentheses. And then inside I'll be left with, if we multiply by 500 inside, 500 minus y. This means I have a carrying capacity of 500, which is reflected only in choice D. Also, the fact that we are starting at 100 means we have to grow up to the carrying capacity rather than growing down to it. So all of these are pointing to choice D.